So, welcome to massive open online course on fluid flow operations. In this lecture, we will discuss about the fundamentals of flow as a part 2. In part 1, we have discussed about the mathematical representation of fluid flow, how it can be represented by Eulerian method or by Lagrangian method, and also we have discussed about the streamline, streak line, path line, timeline, and also stream function and velocity potential, how this velocity potential is related to the stream function, and also what are the different types of fluid flow, like whether it is steady state or unsteady state, if it is viscous or inviscid, that has already been discussed, and also whether the flow is uniform or non-uniform, how the flow is fully developed, and also whether it is laminar flow or turbulent flow, how this laminar and turbulent flow be calculated or can be identified. And also we have discussed something about what will be the basis of the 2 dimensional, 3 dimensional and also 2 dimensional flow. Now, in this lecture we will discuss about the acceleration which will be represented in 3 dimensions, and also what will be the circulation and how it can be mathematically represented, what will be the vorticity and how it can be mathematically represented in 2 and 3 dimensions, and also what will be the angular velocity, how it can be represented, how the pressures or acceleration of the fluid flow can be represented in 3 dimensions, even in single directions also. Now, as a 2, 3 and 1 dimensional case, we can say that this 3 dimensional flow is represented by as a function of x, y, z, that is in the spatial coordinates in x, y and z, and also as a function of time. So, if suppose the velocity of the fluid is represented in the x, y and z directions, then how it can be represented in 3 dimensions? It will be u will be as a function of x, y, z and t. Similarly, in the v, that means the y direction, again it will be a function of in x, y and z direction and also time. If w is the velocity component in the z direction, then also this w can be represented as a function of x, y, z and t. In 2 dimensions also we can represent the fluid parameters, like if liquid is running between 2 parallel plates and cross cut vertically to the plates and parallel to the flow, then we can represent it as u, that is u is the velocity of the fluid as a function of only x and y direction and also as a function of time. Similarly, v will be represented by that in the x and y directions, then it will be x, y and t. For 1 dimensional case, if suppose the liquid is flowing through a narrow tube and its velocity will be average velocity, you will see that there will be no variation of the velocity in the y and z directions except x direction. So, in that case the flow as a velocity component in 1 direction should be represented only in the x, y or z directions, either one. So, u will be a function of only in the x direction, or it is in the y direction or in the z direction, that is u will be the x comma t, that is the time here, or you can say v will be equal to y comma t, or z will be equal to w will be equals to only that is z comma t. So, in this way you can represent the 1 dimensional, 2 dimensional and 3 dimensional flow. Now, let us consider the acceleration of the fluid flow, and to make these calculations for this fluid flow such as pressures and forces, it is necessary to describe this motion of the fluid in details as in terms of what is that acceleration. Now, the expression for the acceleration is needed assuming the velocity field is known to you. Now, in that case, if we consider a fluid particle that have a velocity v t here, velocity v t, at an instant t, then we can say that v should be as a function of x, y, z and t. And if we differentiate t with respect to that spatial coordinates and the time instant, then we can say that dv will be equal to dou v dou x into dx plus dou v dou y into dy plus dou v dou z into dz plus dou v dou t into dt. In this case, this dou v by dou t, if we divide this dv by dt, that means on both sides if we divide, then we can get dv by dt, that is actually the acceleration of the fluid. Now, this will then come, it will be dou v dou x into dx by dt plus dou v dou y into dy by dt plus dou v dou z into dz by dt plus dou v by dou t. Now, this one will be thus dx by dt will be represented by u and dy by dt it is v and dz by dt it is w in the x, y and z direction respectively. Now, see this velocity vector, if suppose the fluid particle is moving in the in this direction at a velocity v t, and after a time t plus delta t, that means here within a small period of time, if the fluid particles just moving ahead, then the velocity will be v as a function of t plus delta t. And in this case, if we represent this as a velocity triangle here, this is the v at t and dt time interval. So, here in this case this is v t, then what will be, this is 1, this will be your just increment of this velocity with respect to dt, that will be represented by dv. So, here if we know this dv with respect to this small time dt, then you can easily calculate or represent this acceleration as dv by dt, which is denoted by a here. Now, if we consider this velocity to be represented by a vector notation, then you can represent this as v will be equal to u I plus v j plus w k. Here u, v and w are the velocity components in the x, y and z direction, and these are scalar quantities. And then dv, already we have discussed that dv will be equal to dou v dou x into dx plus dou v dou y into dy plus dou v dou z into dz plus dou v dou t into dt, and then acceleration will be by this equation, and finally this. Now, you will see if we can see here the two some terms here. Now, up to these terms of this acceleration, that means here the spatial terms here u into dou v dou x plus v dou v dou y plus w dou v dou z, these three terms will be represented or will be called as the convective acceleration. That means, here only due to the fluid flow at a particular time instance, only in the x, y and z directions, but there will be a time will be fixed. But if we consider again these terms here only at any particular directions, that is any x or any, that is there is no actually effect of that spatial locations, then only time, then it will be called as only local acceleration. So, total acceleration will be convective acceleration and the local acceleration. Now, if we consider each component of this acceleration in x, y and z direction, what should be that? Now, in this case v should be in the x direction. If I consider that in the x direction, then this v should be u, and then acceleration in the x direction will be equal to u into dou u by dou x, like this here, and in the y direction it will be dou u dou y, and in the z direction it will be dou u dou z. So, finally, it will be u into dou u dou z dou x, v into dou u dou y plus w into dou u dou z plus dou u dou t. So, here in this, these are the components. So, you are observing here very interesting point that u that means in the x directional velocity scalar quantities also varies with x, y and z directions, and also with time t. So, a x acceleration, then it will be as a function of this. Now, only if you are considering the x direction, there will be no variation of the velocity of u with y direction, then dou u dou y will be 0, and in the z direction if it is not the effective, then dou u by dou z will be equals to 0. So, in that case only in the x direction the a x will be equal to u into dou u dou x and plus dou u by dou t. Now, very interesting that if you are not having any component of the velocity in the x, y and z direction, only u will be there, then at a particular time, then only dou u by dou t it will be equal to acceleration. Similarly, in the y direction the acceleration components will be equal to u to dou v dou x plus v dou v dou y plus w dou v dou z plus dou v dou t. Similarly, in the x z direction it will be represented by this equation. So, we are getting the acceleration in the x, y and z direction, and what should be its components in x, y and z direction. How it can be represented? You can represent it by this equations. Now, the general equations will be equal to this, general equations will be equal to this, and from the general equations we are getting two components here. One is that convective acceleration and another is local acceleration. So, from these general terms you can easily calculate what would be the component of the acceleration or any other variables there. Now, these things can be represented by other important notations. It is called substantial or material derivatives. So, dou capital D v y dt, this is called the substantial or material derivative. So, this substantial or material derivative is defined as u dou x plus v dou y plus w dou z plus dou t. So, in this case this capital D y dt, here any parameter if you substitute, respective parameter it will come here, here and also here. So, if you are considering only v, then it will come v like this. So, the total acceleration will be represented by dv by dt by these substantial derivatives. Next, if we apply this substantial derivative to the pressure. So, what will be that? So, in the x direction the component should be that dp by dt, that will be is equal to here p x dou p dou x plus p y dou p dou y dou p x dou y plus p z dou p x dou z plus dou p x dou t. So, here this dou p x dou x, here the pressure gradient or pressure per unit length in the x direction, how it will be changing. If there is no change of pressure in the y direction or z direction, then you can simply omit those terms and you can consider it. And also for steady state operation there will be no change of pressure, then you can say that the dou p x by dou t, that will be equals to 0. Similarly, in the y direction you can represent this dp by dt, that means variation of the pressure in the with respect to time. In the y direction it will be like this. Similarly, in the z direction the velocity pressure variation with respect to time, it will be represented by this. Now, another important characteristics of the fluid flow, it is called rotation and the spinning of liquid. What is that? Here see the diagram, one video is there. So, from this video you will see how liquid element will be rotated and how it will make a vortex over the surface and how depth of this vortex will be there. By this video you can see. So, fluid element how it will be rotated. If you inject some dye in a rotating surface, you will see these dye particles how it will be forming a streamline, rotational streamline here. So, and then this streamline will be represented by a mathematical expression that will be discussed here, how this rotation will be there and what will be the vortex, what is the vorticity, the terms, what will be the intensity of the vorticity and how this vorticity can be calculated from the rotation of this fluid and it will be represented. So, if we visualize this fluid flow as the motion of a collection of fluid particles, that is if you are considering cube or infinitesimal volume that deform and rotate as they travel along. Now, if the cube deform, but not rotate, if any cube suppose is deform, but not rotate, it will be called irrotational flow. Now, if the cubes do rotate, then they possess some vorticity. Here you will see that vorticity. From this video also you can observe that vorticity. Here see how depth this liquid particles is going downward, and the formation of fluid particles as a tube as cone, and from the bottom, in the bottom you will see the fluid particles will be coming and form a cone shape there, and at the end point there will be one single particles there, and so this way it will be a vortex. Here this is the vortex, and at this particular direction it will be rotating, and this vortex how it will be forming here. And if the cubes do rotate, then they will form vorticity, and fluid particles running through a suppose in a river, you will see sometimes there will be a formation of vorticity that will undergo a rotation and the deformation there. Now, angular velocity and vorticity, what will be that velocity of that rotation? You have to find out, that will be called as angular velocity. Now, if an elementary rectangle of the fluid here in the diagram is considered as A, B, C, D with the sides small sides d x and dy. This is the what is that elementary rectangle here. This is one face of this rectangle, and this one like this. This is your one rectangle. Now, in this case this is one face. Now, ABCD with sides here dx and dy, and AB in the x direction, AB in the x direction moves to A dashed B dashed, moves to A dashed B dashed. Here moves A B is moving to A dashed and B dashed here, and also you will see that other parts also DC will be moving to D dashed C dashed. Now, very interesting that if we twist this, if we rotate this fluid element with a certain angle d epsilon 1, and AD in the y direction rotates by d epsilon 2, one is d epsilon 1 at an angle, another is d epsilon 2, then in this case we can write d epsilon 1 will be equal to dou v dou x into dx dt, and d epsilon 2 will be equal to dou u dou y into dy dt. So, in that case what should be the theta of deformation? That will be represented by, and it will be defined by d epsilon 1 by dx is equal to dou v dou x into dt. Now, d theta 2 similarly from the geometry d epsilon 2 by dy, and it will be minus dou u dou y into dt. So, in this way we can calculate what would be the d epsilon 1 and d epsilon 2, and d theta 1 how it will be related to that. Then from this two deformations of this epsilon 1 and epsilon 2, we can easily calculate this d theta 1, what is the angular deformation of that. So, from that angular deformation we can calculate the angular velocity of AB and AD, which will be denoted by omega 1 and omega 2 respectively, where omega 1 will be defined as d theta 1 by dt, and which will be dou v dou x. Similarly, omega 2 will be dou theta by dou dt, that means per unit time how this deformation is happened. So, it will be minus dou u dou y here. Since in the counterclockwise this movement is there, there will be a negative, and also for center O, if we consider the average angular velocity is omega in the z direction, then in the z direction of angular velocity will be represented by omega z, which will be average of this deformation in angular deformation of omega 1 and omega 2. So, average of this half of omega 1 plus omega 2. Now, if you substitute this omega 1 and omega 2 from this and this equation respectively, then we can simplify and get this equation of omega in the z direction, that is angular velocity in the z direction. It will be is equal to what is that, half of dou v dou x minus dou u dou y. So, this is your angular velocity. So, you have to remember this angular velocity, how to calculate if you are deforming this any face of this element of fluid with an deformative angle of d theta 1 and d theta 2, and for which that angular velocities of omega 1 and omega 2, then you can represent this the average angular velocity by this averaging of these two angular velocity of this. So, in that case finally, we can say that this angular velocity will be equal to half average of this two angular velocity, and which will be represented by the Cartesian coordinates of this dou v dou x. That means, what will be the velocity in the y direction is with respect to the distance in the x direction, and also the velocity change of y direct of x direction with respect to the distance of the y direction. That means, it is called, this terms it is called velocity gradient. So, this velocity gradient in the x and y direction. Now, summation of this velocity gradient of this y direction and in the x direction, that will be represented by this angular velocity here. Now, from this this part of this angular velocity only, the relative gradient of this relative gradient of this velocity of this y and x direction, it will be represented as the vorticity here. So, vorticity is defined as dou v dou x minus dou y in the z directions. So, here we can say that this is only that what is the relationship in the z direction angular velocity and the vorticity. So, omega z will be equals to what, 2 times of angular velocity. So, omega z is the vorticity. So, very simple, vorticity vector will be, or vorticity will be equal to 2 times of angular velocity. Now, other components of the vorticity can be represented by this omega x, that will be the x direction, it will be dou omega y, dou w dou y minus dou v dou z, and also in the y direction this vorticity will be dou u dou z minus dou w dou x. So, this will be your vorticity in the other x and y direction respectively. And also by vector components, you can say by vector notations you also represent by these equations, and also angular velocity in the x direction it will be like this, and in the y direction it will be like this. So, resultant angular velocity will be root over of that square of this angular velocity in the summation of angular velocity in the x, y and z directions. So, here this represented by this equation. So, it will be square root of angular velocity in the x, y and z direction and its summation of the square of the angular velocity. Now, vorticity vector, if we are considering the in the vector, that means in the general notation in x, y and z direction, then omega vorticity will be equal to 2 times of angular velocity. So, in this case very interesting that you have to remember also for irrotational flow, angular velocity and the vorticity will be 0. So, if you are getting irrotational flow, that means here there will be no angular velocity, there will be no vorticity there. As an example, if we consider this, if the velocity component at a point in a flow rate u, that will be equal to a plus b y minus c z, and v will be equal to d minus e z, and w is equal to a plus c x minus e y here, where a, b, c, d, e, f are constants. Now, in this case you have to tell whether the fluid is moving as an irrotational flow or rotational flow. If it is not irrotational flow, then calculate what should be the rotation and vorticity of this fluid flow. Now, first you have to calculate the component of the rotation. What are the components? This omega x, that is in the x direction, it will be half of dou w dou y minus dou v dou z. So, it will be half of, now dou w by dou y you can calculate it from this equation, w is equal to a plus c x minus c y by derivative, by its derivation. So, here dou w dou y it will be minus e and dou v dou z it will be minus e. So, here minus e minus of this minus e, that will come 0. Similarly, in the y direction omega will be equal to minus c, in the z direction omega will be equal to minus b. Now, finally, the resultant, this angular velocity will be equal to root over of omega x square plus omega y square plus omega z square, that will be equal to root over of, after substitution of this omega x, omega y and omega z, it will come root over b square plus c square, which will not be equals to 0. What does it mean? The flow is not irrotational, it is rotational flow. So, in this case what should be that? Rotation and vorticity. Now, rotation, this is the rotation, root over b square plus c square. Now, what should be the vorticity? Vorticity will be equal to 2 times of rotation, that means omega will be equal to 2 of omega, this is simply 2 into root over b square plus c square. This is in terms of radian per second. Now, another important characteristics, it is called circulation, that is Stokes theorem. As per Stokes theorem, we can consider here that if you consider a closed curve here in a streamline of fluid flow as shown in figure here, the integrated V s dash, this integrated V s dash is nothing but the velocity component in the tangential direction of this velocity V s. This velocity is V s, now its tangential will be V s dashed, now at a given point in the curve. Now, the integrated V s dash at a given point on this curve along this same curve is called the circulation. This circulation will be denoted by omega, sorry, it is represented by gamma. So, this gamma will be represented by this integration of this B s dash d s, and this B s dash is nothing but the if it is making an angle theta, then it will be V s cos theta. So, after substitution of this B s cos theta, it will come here like integration of V s cos theta d s. Now, if we divide the area surrounded by this closed curve S into micro areas, the circulation gamma of one such elementary rectangular ABCD here in the diagram, area dA, we can express d gamma will be equals to u into dx plus v plus dou v dou x into dx into dy minus u plus dou u dou y into dy into dx minus v dy. That means, here in this direction what will be that u into dx, in this direction here it will be v plus dou v dou x, because this velocity will be changing with respect to x here, and into dy, and minus here in this direction the x directional velocity, in this case here u plus dou u dou y, because in the y direction this velocity will be changing, that is why the gradient will be dou u by dou y into dy, and then you have to multiply by dx here, because here some distance will be there, area. Then after that here it will be what is that, minus v dy, this is v dy. So, this is the resultant, what is that, circulation in this case. So, finally, after simplification you can say dou v dou x minus dou u dou y into dx dy, that means nothing but this portion is omega and this portion is nothing but this area. So, this omega into area will be represented for the circulation of this fluid element here. Now, the circulation is equal to the product of this then vorticity and area. After integration you can have this gamma will be equal to V s dash d s, then V s into d s by integrating whole surface of this element. Now, the surface integral of vorticity is equal to the circulation. This is the statement. This relationship was introduced by Stokes and is called Stokes theorem. In a closed curve, there will be no vorticity, no circulation. Let us do an example for this, like the circulation if we represent by if suppose a circulation is happening through the surface of the circle, or circulation happens in such a way that we can represent it as a circle, and what will be the equation of that circle, that will be x square plus y square minus 2 a y equals to 0, where a is the radius of the circle and is situated in two dimensional flow with u is equal to k y and v is equal to 0. Now, in this case what should be the circulation about the circle, and also k is an arbitrary constant and a is the radius of the circle. By considering it, what should be the circulation velocity there. So, in this case if we consider that gamma is nothing but as per theory it will be w into a, that means vorticity, that means vorticity into what is that into area, and area is nothing but pi a square since it is a circle, and omega is the vorticity, it is dou v dou x minus dou u dou y. So, here dou v dou x is nothing but 0, because we are getting from this u is equal to k y. So, here there will be no change of velocity in the x direction. So, here dou v dou x will be equals to 0, whereas dou u dou y that will be equal to minus that will be equal to k, because this u is changing with respect to y, that is in the y direction, then it will be minus k after derivative of this equation of u is equal to k y. Then finally, it will be coming minus k. So, gamma will be equal to, that means circulation gamma will be equal to omega into a, that will be minus k into pi a square. Also, in the second method you can calculate another way, like that gamma will be equal to integration of this u into dx, because in the x direction you are getting that circulation. So, in this case in the y, how it will be changing u into dx, that will be k into y into dx. So, overall based on this circle, if you substitute this k and y here y is nothing but here a into 1 plus sin theta into minus a into sin theta d theta. You can have it from the geometry like this, u t if it is a into cos theta 90 minus theta here as per diagram, then x will be equal to a cos theta and y minus a will be equal to a sin theta. Here based on this you can say that what should be the value of y will be equal to a into 1 plus sin theta and dx will be equal to minus what is that a sin theta d theta. So, after substitution and getting the integration with within the limit of 0 to 2 pi, we can get minus k into pi a square, that will be as meter square per second it is. So, we can get this then circulation based on this vorticity and also the rotational. If there is a to represent the circulation in terms of angular velocity, that also can be possible, because the angular velocity and the vorticity is directly related. Then angular velocity, from the angular velocity you can calculate the vorticity, from the vorticity you can calculate the circulation. So, those are related to each other. Very interesting that here we have already discussed that how this circulation or angular velocity is related. Angular velocity is the that is half of vorticity, and also vorticity is related to that circulation, as vorticity we multiply with this vorticity by cross sectional area, then you can get the what is that here the circulation. So, I am just suggesting to for the reading here from the Fox McDonald textbook for fluid mechanics, and also McCabe Smith you can follow, that is Unit Operations of Chemical Engineering, 6th edition or higher edition also you can follow. There also some this fluid characteristics are described, and mostly for this other part of the circulation and even transport different processes you can get in details also from this textbook of Bird, Stewart and Lightfoot, that is transport phenomena, and any other textbook you can follow for more in details, but this is the basis for this this circulation, vorticity and the rotational velocity. So, thank you.